Hi folks, chapter 17. Alright, chapter 17 is all about change of phase. Now we've learned previously that there's 4 phases of matter, right? Solid, liquid, gas, plasma. Okay? We're going to deal mostly with just solids, liquids, and gases. Alright, we're going to learn how they change phase, meaning change from one form to another, from solid to liquid, liquid to gas, and vice versa. Alright, that means we got to talk about evaporation, condensation, boiling, melting, freezing, all these processes and what actually is going on in there energy-wise. Alright, there's a little flow chart right here to help you get the idea. Okay. So what phase a material ends depends on temperature and pressure. Alright. So ice obviously is a solid. That happens at a lower temperature, right? Water vapor is a gas. That obviously happens at a higher temperature, right? Pressure plays a factor too, and we'll get to that later. All right. If there's a change in temperature, then there's going to be a change in the energy as well, right? Because we know from previous chapters that temperature is directly proportional to that kinetic energy of the molecules. All right. So if we increase the temperature, that means we're increasing the energy. It means molecules are going to move more and have more collisions, right? When this happens, then materials will change from solid to a liquid to a gas, and then if we go a step further, plasma, all right? So that means we got to have some kind of heat source, some energy inputted into the system, right? This requires energy to happen, okay? Well, and we can go the opposite way too. If we take energy away, like we see in this chart here, if we take energy away, then we cool gas down to a liquid. If we take more energy away, we cool it back down to a solid. Okay? That's the flow we're going to be dealing with. Okay? So evaporation. This is one of the first steps we're going to discuss. It changes liquid to a gas. Right? Well, here's how it happens. We got all these molecules in here, bebopping around, right? Continually moving, having all these collisions. All right? Well, these collisions will impart energy to one another, right? Some may gain some energy, some may lose some energy. So if we get molecules that gain enough kinetic energy, then they can escape being a liquid and they can turn into being water vapor. All right? Now, these molecules that escape to become a gas, they take their energy with them, right? So that means you're putting energy over here and you're taking some away from over here, all right? So that means the average energy left on the liquid side of this picture is less, right? Okay, so if energy decreases, temperature decreases, right? So you actually have cooler water, right? Evaporation is a cooling process. Okay, very important that evaporation is a cooling process because that's why we sweat, right? You have this water, right? Sweat stuck on your skin. It absorbs the body heat, right? And then the air evaporates it off and takes that heat with it, and that's how we cool down. Okay? All right, condensation is the opposite of evaporation. All right, you have this water vapor over here, this gas, all right? And the gases are bebopping around, colliding, and again, some gain energy, some lose energy. Well, if they've lost enough energy, and if they come close enough to a liquid surface, then they can go and be right back in there as a liquid, all right? So this adds energy to the liquid side, right? Takes it from the gas, adds the energy to the liquid side. So what does that do? It warms it up. Adding that energy increases the temperature. Here's some examples of condensation and how it works. All right, with a little video there for you. All right, condensation is in the atmosphere. All right, this is how we get fog. All right, and low-lying clouds. All right, it happens up there too. All right, boiling. Boiling is rapid evaporation that happens beneath the surface of a liquid. All right, so look at this. We got the heating element on our stove, right? It's going to cause this water on the bottom of the pot to increase in temperature first, right? Well, that'll cause little bubbles, right? You ever notice that? Bubbles along the bottom of the pot when you first start boiling things? Okay. Well, if the pressure, vapor pressure, because there's air, gas inside those bubbles, right? If that vapor pressure is less than the water pressure surrounding it, then that bubble's going to pop, right? And it's going to collapse right back down, all right? But if enough energy gets put in there and you have enough increase in temperature that bubble's got enough vapor pressure, it'll rise to the top and then pop at the top, and that heat escapes, right? That is boiling, okay? All right, so here's another picture. We've got our bubbles in there going. All right, water boils at 100 degrees Celsius at sea level, okay? This shows water in thermal equilibrium, right? We've got the heat set just right to where this water stays 100 degrees. Now it's boiling, all right? But because it's at 100 degrees and not above that, that means as much energy that's getting input into the system from the heating element is the same amount of energy that is escaping, all right? So therefore the equilibrium, right? You'd have to increase the heat or have some kind of change to get over that hump, okay? Now I mentioned sea level, right? Now remember I told you that the phase of matter depends on pressure, right? Well, what happens when you get higher in elevation? We touched on this a few chapters ago. That atmospheric pressure gets less and less and less and less. So the less pressure, that means boiling happens sooner, right? Boiling point depends on pressure. The lower the atmospheric pressure, the lower the boiling point. For example, 95 degrees in Denver, which is, mile high, versus 100 degrees at sea level. All right, little video on that for you too. All right, melting and freezing. Of course, they're opposites, right? Melting occurs when we go from solid to a liquid. All right, heat is added to the ice going along with this picture. All right, what's that doing in there? That's making those bonds holding that ice together jiggle and vibrate more and more and more and more, right? They're getting that energy in there, that temperature's going up, the energy's going up until finally the bonds can start breaking. And then we have phase change to water, all right? Well, the opposite happens with freezing. You take enough heat out, and the molecules start getting closer and closer together until finally they're close enough that these bonds can form, and then you've got ice. All right? So here's a good diagram that I like to demonstrate phase changes, okay? Now, energy is absorbed, all right? And phase changes go left to right, all right? That's what this top arrow means, right? You're adding energy to the system. That means solid will become a liquid, liquid will become a gas, right? Now, look at this bottom arrow going to the left, all right? Down here, if we have energy released from the material, right? We take energy away out of the material, then we're going to have a gas go to a liquid, liquid go back to a solid, all right? So whether you're adding energy or removing energy will depend on which phase you go to next, all right? Okay. Now, latent heat of fusion is the amount of energy needed to change any substance from a solid to a liquid or a liquid to a solid. It goes either way, right? That road travels both ways, right? Heat of fusion for water is 334 joules per gram or 80 calories per gram, okay? Latent heat of vaporization is the amount of energy needed to change any substance from liquid to gas or gas back down to liquid, all right? Again, two-way street, all right? This takes more energy, 2,256 joules per gram or 540 calories per gram. All right? It takes a lot more energy to make a gas than it does just to make a liquid. Okay? Now, what does latent mean? Okay, now that we got some numbers, let's dig into it a little bit more. Latent means hidden. Well, how do you hide heat? Well, when a substance is changing phase, it's breaking those bonds, right? Or, if you're taking energy away, it's making those bonds, right? So something's happened on the molecular level. Well, that means that temperature stays the same. No increase, no decrease in temperature when you're changing phase, because all that energy is going into changing the bonds, all right? That's why it's called hidden heat, because you can't see it through a temperature change, all right? This chart shows it really well. when you have an increase on the line, right, that means temperature's going up. But look right here, you're melting the ice, it stays flat. All the energy's going into a phase change. All right, here, increase it up to the boiling point, and then look at all this energy, 540 calories it takes. All right, that's a big flat line. It takes a whole lot of heat to change that phase, right? And once we're changed all over to steam, then we start increasing our temperature again. Okay? Well, we talked about heat before when we used this equation, right? Previous chapter. Well, now we need a way to find that hidden heat too, right? Because we know it takes 540 calories to heat 1 gram of water up to steam, right? To make steam, to change it over. Well, what if we got more than 1 gram? How do we do that? Well, you use this equation here. The amount that you have, the mass of the substance that you have, times the latent heat. All right? And I've got them written for you here again. 80 for fusion, which is solid to liquid, liquid to solid, or vaporization for water to gas or gas back down to a liquid. Okay? And there you go. So here's a little practice for you. Here's a chart that you can practice. This is in your book as well, right? So just fill it in and just see how much energy it takes to go from 1 gram of ice to 1 gram of steam, right? Just a little fun practice. All right, and you saw the extra credits throughout there and the videos throughout there. So check those out, read your chapter, all right? And always, if you have any questions, let me know.